Tell me when I'm ready. I mean, just tell me. All right, so now, so up to this point, we've been talking about fluids at rest. Now we're going to talk about fluids in motion. And I have to say, this is incredibly complicated. The mathematics is horrendous. However, we're only going to talk about the ideal cases, right? So we're going to only, ideal cases. So we're going to use something called an ideal fluid flow model. So what does that mean? Remember, this is liquids and gases. And so we're going to say that the fluids are incompressible. Now you should say, what are you talking about? You can compress a gas, right? Well, actually, gases in motion are pretty close to being incompressible. We're going to say there's no viscosity, there's no friction, like molasses has viscosity, or like oil that's been cold, motor oil, has viscosity. No viscosity. And we're going to say a constant velocity pattern. See how here's the fluid moving, and the velocity is the same everywhere along the fluid. Okay? So it's an ideal fluid. Blood is not an ideal fluid. Okay, so here, this is called viscous fluid flow. This is not ideal. So you can see that the velocity is maximum here in the center, and then it gets smaller and smaller. And the reason is because there's viscosity. Like, think of, it's sticking to the sides of the tube, right? The velocity is 0 on the walls. So we'll talk about this just a little bit, but we're really going to key on ideal fluid flow. So there's only, for ideal fluids, there's really two major equations. And they're nice and, well, they're kind of fun, you'll see. All right, so here we have a tube or pipe. And whenever we have a pipe, no leaks, okay? Because that would sort of wreck everything. So here we have a certain volume of fluid. And it's going to go from this area to this area. And we want to discuss what happens. Now, obviously, this is the same, this and this, right? The same volume, right? I mean, that's because there's no leaks, so the same volume. So we have V1 equals V2. By the way, when you're doing these problems, you got to be careful. When you're talking about volume, make sure your V's are large. When you talk about velocity, make sure you use small V's or you're going to get totally confused and it's going to be a mess. Okay, now, again, we're moving this fluid, right? We're moving the fluid. So we're going to say, during some time, during delta t, during some time interval when the fluid is moving, we're going to say that V1, okay, V1, what's the volume of this thing? It's just a cross-sectional area, A1 times X1. So V1 is cross-sectional area A1 times X1. And V2 is this cross-sectional area A2 times X2. Kind of makes sense, right? Okay, now, what is X1 and X2? Well, this is a chapter 1 or 2 kind of question, right? We know that distance equals speed times time. So therefore, X1 equals V1 delta t, and X2 equals V2 delta t. All right, so therefore, V1 equals A1 times V1 delta t, and V2 equals A2 V2 delta t. It's the same delta t's, right? Okay, now remember, these are equal, right? These are equal. So I have A1 V1 delta t equals A2 V2 delta t. Well, what can I do to the delta t's? Goodbye. So delta t there, goodbye. Delta t there, goodbye. So I have A1 V1 equals A2 V2. That's the equation, right? So that's called the continuity equation. You can write it however you want to write it, as long as it's one of these. So A1 V1 equals A2 V2. We can just say AV1 equals AV2. Or you can just say that AV is constant, right? I mean, it's the same thing, right? So no matter where you are along that pipe, AV is always going to be constant. Simple as that. Now, if you go, I don't know, if you like fishing or something like this, you probably know this. So what's that all about? Okay, still water runs deep. So let's say you're on a canoe and you're on a river and you're trying to fish you want to get fish that really like being deep, okay? So here's the river. So we're going to look at, so here's the top of the river, right? And here's the bottom, okay? So and this is all water, right? And then let's say the river always, okay, so here's the river. Then let's say that the river goes like this, all right? Okay, now remember, so A1V1 equals A2V2. Remember, the A is the cross-sectional area. So here, compare the A's. Here, this is A, well, just pi r squared, right? Or however it's not going to be pi r squared, but the cross-sectional area here is much, much less than the cross-sectional area here, right? Okay, so this A2 is much bigger than A1. But this has to equal that. So it has to be true about V2. It has to be really, really smaller. So if the velocity here of the water is really, really small, that's what they mean by still water, right? The water can be moving kind of quickly here, but then when it gets to this point, it's going to start going super, super, super slowly. So if you're trying to get fish, that like being really, really deep, you're going to wait until you get to that part of the river where the water is hardly moving at all. And then you know it's super deep, so you can go fishing. Ta-da! There, learn something new. Learn something useful today, right? Okay, now here are some things that you'll see in your homework and maybe tests or something like that, or when you read the book. So AV, let's look at the units. So AV, okay, A is the cross-sectional area, right? So it's meters squared. Velocity is meters per second. That's meters cubed per second. Well, what's a meter cubed? It's a volume. So this is a volume per second. So AV, the change in, so you look at velocity, volume. So AV is the change in volume over the change in time. That's called the volume flow rate, right? Volume over time. Whenever you have something over time, it's a rate. So it's a volume flow rate, meters cubed per second. Now, if you multiply that by a density, let's do it. Let's see what we come up with. So now we have a density times delta V over delta T. So density is kilograms. I'll just say, whatever. I'll say mass. I'll just say, mass per volume, right? And then volume, delta V is volume, delta T is time. So the volume is killing, you get mass per time. So that's called the mass flow rate, kilograms per second. So, you'll see these terms. The question is going to say calculate the volume flow rate. It just means calculate AV. You multiply that by, if they say calculate the mass flow rate, it's just AV times the density. So you'll see that. All right. So this is the first, like I said, there's really two major equations with fluids in motion. That's the first one, called the continuity equation. AV equals constant. Continuity equation. Now the second one, it's going to look awful, but it's not so bad. So just hold on. Well, okay, here's a question first, though. All right, so here's a faucet. You turn on the faucet and the water starts flowing. And where is the speed of the water the greatest? Now, pretend you don't know anything about gravity, okay? So forget about gravity. Just use the continuity equation. Look at the water and look at this formula. Where's the speed of the water the greatest? So pause your videos and figure it out. Okay, we're back. So you can see that the cross-sectional area here is larger than the cross-sectional area here, right? So therefore, where does the speed have to be larger? Well, again, this is large, this is small, but this product equals that product. If this gets smaller, this has to get larger. So the answer is at the bottom. Okay, now pretend, okay, now we do know about gravity, right? So we know why it's faster here than here because of gravity, right? Because of gravity. But anyway, that's kind of cool, right? You just, every time you see water coming out of a faucet, if you, have a nice long stream, you can demonstrate this equation. So that's kind of nice. All right, now we're going to learn the second important equation with fluids in motion. All right, this again is a pipe or something like that. And we know that AV equals constant. So please use this fact and answer the question. So pause your video and answer the question. Okay, so let's answer the question. So this A is bigger than this A, right? So here, let's do it like this. We have AV on the left equals AV on the right. Okay, so here we have A on the left, and then the A on the right, goes way small. But again, this product has to equal this product, so what has to happen to this one? It has to increase, right? So V2 has to be greater than V1 because of the continuity equation. Now, so that means, okay, hold on a second. So you can see that these vectors are longer than these vectors, right? Indicating that V2 is greater than V1. Now, all right, so V2 is greater than V1. Well, that means that the acceleration vector points to the right. Agree? Because the velocity is to the right and the speed is increasing to the right, so the A has to point to the right. We learned that a long, long time ago. Wow. Well, if there's an acceleration to the right, according to Newton's second law, there has to be a force to the right. What's causing it? I mean, there's no little alien, pushing it or something like that. What's causing the force to the right? Well, what's the only thing available? Pressure, right? And we know that pressure equals force over area. So there has to be a pressure. So this pressure has to be greater than that pressure, right? Agree? So here you go. All right? So the pressure here has to be greater than the pressure there because we want a net force this way, right? Net force that way for that. Okay, now, wow, is there some kind of relationship with the pressures? Well, yeah, there is. Oh my gosh, don't have a heart attack. So it's called Bernoulli's equation. Pressure plus density Gy, this is like the elevation of the pipe, plus 1/2 rho v squared at location 1 equals the same thing at location 2. So if you can write it like that if you want, or you can put the subscripts individually. We're saying the same fluid, so you don't have to subscript the rho. All right? Or you can just be totally lazy. Just write it like that. This plus that is constant. It never changes. Right? It never changes. Now, we want to make this simple because it looks awful. So let's just say that the pipe is horizontal. Well, that means that y1 equals y2. Well, we already know that the densities are the same, and of course G is the same, so we can just get rid of this, right? We can just get rid of that. Goodbye. And now we just have, so instead of having that, we get rid of this, now we just have that. And this is really what we want to concentrate on mostly. I mean, you might have a problem where you have to use that, I don't know. You may in the homework, but right now we just want to concentrate on this. So I just said y equals 0. Because remember, we're allowed to call y equals 0 wherever we feel like it. Okay, now this is totally cool. The pressure plus 1/2 rho v squared is constant. All right, so what does it mean? What does it mean? So if you can somehow suddenly increase the velocity of the fluid, like the air, what has to happen to the pressure? It has to decrease. Remember we talked about the vacuum cleaner? I explained the vacuum cleaner. You have a fan inside here somewhere, and it basically gets the velocity of the air going really, really, really fast. And therefore, what happens? What does Bernoulli just say? Bernoulli says if you get the velocity going really, really, really fast, and look at it, it's v squared. So, I mean, so this term is going to increase a lot if you increase the velocity. So if you increase this, remember this sum has to be constant. So if you increase this, then this has to decrease. So in the vacuum cleaner, the pressure in here is much, much less than the atmospheric pressure. You use the beta bar to get the dirt up in the air. Then you have all this atmospheric pressure outside, which is much, much larger than the pressure inside here. So the atmospheric pressure just pushes the dirt up here. That's how a vacuum cleaner works. Pretty cool. Okay, so I have a demonstration for you. Okay, so this is just an ordinary piece of paper, right? I'm not cheating, just ordinary piece of paper, you know? Okay, so what am I going to do this? Watch. And okay, so if I try to do this, it doesn't really move much. I mean, it doesn't, So watch. And I'm not going to move my hands. You see. Okay, I was blowing on top of the paper, and the paper did this. Why? Why did that happen? Bernoulli, right? Bernoulli. Oops, sorry. Okay, so what did I do to the velocity of the air here when I blew? So this, it increased, right? So this increased, so therefore this had to decrease. Now look at, down here, it's just atmospheric pressure, right? Just normal everyday atmospheric pressure. Here the pressure decreased, so therefore this pressure was greater than this pressure, so it went up. So that's how it worked. Okay, that's what happened. All right, let's see. Let's do another one. Yeah, okay. No. Okay, let's do this one. Okay, this is just a funnel ping pong ball that somebody painted. Just an ordinary ping pong ball. There's no glue on it. I'm not cheating. I promise. Okay, so watch. So again, if I put it like that, it's going to drop. No kidding, right? Gravity. So watch. What's the deal with that? Okay, what was I doing? I was blowing, right? I was blowing. So, how did the velocity of the air here compare with the velocity of the air here? Well, here I was blowing like crazy, right? And so here we had high velocity. Here we had, I don't know what you call it, like regular velocity, I don't know, regular, you know what I mean? So here we had high, here we had regular, whatever that is, right? And so here, high velocity. So the pressure is low. So low pressure. Here we just had regular, ordinary P atmosphere. So in other words, the pressure here was greater than the pressure here. So what happened? The ball just sat there, Pretty cool, right? This is a problem in Hawaii when you have the tornadoes or hurricanes, I guess, hurricanes. So, if you have these incredibly high winds, sometimes you read in the newspaper that people's roofs are blown off. That's kind of a problem, right? Why does that happen? So here's a house, one-story house, and you have these horrendous winds. All the windows are closed, right? You have these horrendous winds. So the velocity of the air here is enormous compared to the velocity of the air inside the house. Well, if this gets super, super high, the pressure gets super, super low. So the pressure here is much, much less than atmospheric pressure. Inside the house, you have atmospheric pressure. Outside the house, you have super much less than atmospheric pressure. There's a net force up, and if you don't have your roof attached with extra braces like they do in Hawaii, goodbye roof. And so that's what actually happens. That's why, again, in Hawaii, they usually have straps, metal straps, so you strap down your carport roof and your house roof and your garage roof and all that, because that's such a problem. Here you see this on the highway. So let's say you're a truck driver and you don't want to lose any of your load, obviously. So you have this tarp and you put it on as tight as you possibly can, right? You know, you just put that thing so it's super, super tight. Okay, now the truck is moving along the highway and you're watching it and you're saying, whoa, look at that tarp, it's bulging outward. Well, why is that? Well, here the air is moving, right? Well, let's put it this way, you're moving relative to the air, which is the same thing as having the air move relative to the truck. So inside the truck, the air is stationary, atmospheric pressure. Outside the truck, the air is moving relative to the truck, so the velocity is high, pressure is low. Inside you have atmospheric, outside you have low pressure, bingo, tarp bulges outward. So that's just another demonstration of the Bernoulli effect. Okay, now we're going to do the tough one. Okay, so here we go. So this, I'm going to demonstrate something which is going to demonstrate the continuity equation as well as Bernoulli. Yeah, I should have just said that. Okay, so I'm going to demonstrate both of these equations with this one demonstration. So it's kind of neat. All right, so here, oh man, did I just, so they can see that? Okay, so you notice that here the tube is wide, and then here the tube is narrow, and then here the tube is wide. So it's kind of like this. So it's wide, narrow, and then wide. Okay, so we have AV is constant. So here, the A is larger than here, right? So let's call this A1 and V1 and A2, V2, right? Just this part. There. All right, okay? So A1 is big, A2 is small. Therefore, what has, so A1 is larger than A2. Therefore, V1 has to be less than V2, right? Agree? Because the product is the same, right? The product is a constant. So here, the speed is going to be greater than here. But what does Bernoulli say? When the speed increases, the pressure decreases. So what should you see here? Right? So again, fast speed, so low, no, high, what did I just say? Fast speed, so low pressure. So right now, you can see that the levels of water are the same, but since there's less pressure here, what should happen? This one is going to, well, you'll see, these two, there's going to be more pressure here than here, so these two should drop. Let's see. This is physics. Do an experiment. Okay, did you notice it? So the pressure here is less than the pressure here. So these two should have been, this one and this one should have been lower than this one. Could you see it? Okay, great. So this is a nice little thing, right? Demonstrates two laws. Okay. All right, so questions for you. Okay, blood flows through a coronary, yeah, if you're a health person, or actually just anybody, you want to pay attention to this. Blood flows through a coronary artery. which is partially blocked, not a good thing, by deposits along the artery wall. So if you eat garbage food and you have a lot of cholesterol and other horrible things, you're going to get blockages in your artery, which is not a good thing. Okay, through which part of the artery is the speed flow largest? So what does that have to do with anything, right? Well, there's speed, and you can see different cross-sectional areas, right? So there's a continuity equation problem. So pause your video and figure it out. All right, as we've seen before, here there's a large cross-sectional area. Here there's a small cross-sectional area. So since the area gets smaller, the velocity has to get larger. So the velocity is larger here than it is here. Okay? So it speeds, goes so like this. All right? Okay. Now, a blood platelet drifts along with the flow of blood through an artery that is partially blocked by deposits. As the platelet moves from the narrow to the wider, what happens? Well, again, this speed is going to be greater than this speed, correct? And when you have fast speeds, you have low pressure. So what's going to happen then, right? So this is fast speed, because of this, compared to here, I mean. Fast speed means lower pressure. Now it's slowing down, so greater pressure, increase in pressure. All right. All right, this is a little extra, but it's kind of interesting. An aneurysm is an abnormal enlarged. Oh, I forgot my most important demonstration. I always do that. Forget about the aneurysm. We'll talk about that in a minute. So I have a demonstration here, but I have to give you a little background. So when I first came to BYUH, for whatever reason, they wanted me to give a little physics demonstration for the freshman orientation. So I said, fine. You know, we talked about the Bernoulli effect, how airplanes fly and so forth. But then I brought this demonstration. So this is just, you know, a bag, right, which is tied at one end. And so I explained to all the freshmen and transfer students that we were going to have a contest. So the contest is who can blow this thing, who can inflate this thing with the least number of breaths. So that's the contest, right? So I would look at the students and I would choose the big giant Polynesian, right? And then he would come down and I would say, okay, the winner is the one who inflates this with the least number of breaths. And then I would look at him and I would say, and I'm going to win. And all the students would look at big giant Polynesian and me, and they would laugh. Brother Weber, you're crazy, right? So then the Polynesian kid, or the big guy, didn't matter if he's Polynesian, just a big kid, right? So then the big kid would go like this, and he would just blow, you know? And it would take like 25 breaths. And then I would do it a little differently. Okay, so this is what I would do. Hold it like this. And I would do it in one breath, or maybe two. Thanks. Thank you. Now, and people would be astounded. How can I do it in one or two breaths, and this big kid took him 25? What's the deal? Well, I use a Bernoulli effect, you know, or the Bernoulli law. So basically, when you do what I did, right, like this, what did I do? I blew as hard as I could. So I'm increasing the velocity of the air, right? And therefore, the pressure inside this is less than the outside atmospheric pressure. So that means, since the pressure inside is less than outside, that means that air is just being forced into the tube. And so it just Bernoulli, you know? Anyway, I always forget to do that. All right, let's talk about an aneurysm. An aneurysm is an abnormal, so here's your normal aorta, okay, is an abnormal enlargement of a blood vessel, such as the aorta, right? Aorta with a large abdominal aneurysm. Suppose that because of an aneurysm, the cross-sectional area A1 of the aorta increases to a value of 1.7 A1, right? So here's A1, the cross-sectional area. This is 1.7 A1. Looks like more than that, but whatever. The speed of the blood through the normal portion of the aorta is 0.4 meters per second. Assume that the aorta is horizontal, person lying down. Determine the amount by which the pressure in the enlarged region exceeds the pressure in the normal region. All right. Now, I told you earlier that blood is not an ideal fluid, but yet we're using the ideal fluid rules. That's okay. This is just an approximation. Okay. Now, the question is, how much does the pressure here exceed the pressure there? So, you know, pressure, that's a Bernoulli question, right? But when you look at the Bernoulli formula, there's a velocity in there, right? Velocity squared, in fact. So before we can use the Bernoulli equation, we have to use continuity equation to get the velocity. And that's typical, all right? You should expect that when you do your homework and your exams, your exam questions on fluids. Whenever you have a fluid in motion problem, it's probably going to take the continuity equation as well as the Bernoulli equation. Okay, so first thing, we have to get the velocity. Okay, so there's our two equations, right? And as I said, the Bernoulli equation has velocity, so we got to get that. All right, let's do that first. So we know that A1 V1 equals A2 V2. What we want is V2. Well, right? We want to know V2 in terms of V1. So therefore, V2 equals A1 over A2 times V1. And we can figure, so we have A1, so A2 is 1.7 A1. So that's nice, right? They just give us the ratio. We didn't have to do any pi r squared or anything like that. And V1 is 0.4 meters per second. So we plug that all in, and you get 0.235 meters per second. So just like we expect, right? If the cross-sectional area increases, the velocity decreases because of this. And you can see that this is certainly less than the 0.4. Okay, so that's cool. Now we want to do the Bernoulli. Oh my gosh, right? So let's just write it down. So P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Now we want to see how much P2 exceeds P1. So what we really want, P2 minus P1, right? So P2 minus P1 equals 1/2 rho V1 squared minus V2 squared. So let's do it. So we have 1/2 density of blood, 1060. And then the V1 squared, 0.4 meters per second squared minus 0.2. And you do that, and you get 55.5 pascals. Now, so that means that the pressure here is 55.5 pascals greater than the pressure here. Now, pretend you're a medical type. Look at here. You have the wall of the artery. It's already stretched, right? It's already stretched. So it means it's weakened, right? It's weakened. And then you have an additional pressure. So what happens if you have a weakened, thinned out artery that has excess pressure? What could possibly happen? It could burst, right? It could burst. And that's why people die with an aneurysm. You can have aneurysms in your heart, you can have them in your brain, and they usually, I mean not always, but often they're fatal. So not a good thing, not a good thing. Okay, So we've been talking about ideal fluid flow. Now let's talk about viscous flow. So that's non-ideal. So see, remember we talked about this? Here the velocity is constant everywhere, right? Here this is viscous. So there's really no velocity right here. Then it gets faster, 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 faster. And this is, here, this is a good, right? So this is a good model for blood. Okay, for blood. But you can't really say that either. I'll get to it. Just hold your horses. Okay. So the question is, you know, where do you decide, or how do you decide if it's viscous or non-viscous? So now you got to think back. Chapter 5, Reynolds number. Remember Reynolds number? We learned about drag, the two types of drag, inertial drag and viscous drag. We had these equations. All right. So you got to refer to this again. I mean, sorry, but it's true. Okay. So let's do water flowing in a river. Well, water flowing in a river, the Reynolds number is like 1,000,000. So that means that obviously inertial is way bigger than viscous, right? 1,000,000. So we don't have to worry about viscosity, right, with a river, and that kind of makes sense. How about blood in a large artery? In a large artery, the Reynolds number is still pretty big, so we can ignore the viscosity. But how about blood in a little tiny, tiny artery? How about that? Well, then the Reynolds number is like 0.01. Now that means that the viscosity is greater than the inertial drag. So you can't ignore viscosity, right? So when the blood's going through a little tiny blood vessel or whatnot, you can't use it as an ideal fluid. You have to include viscosity. Oh my gosh. Now, here's an equation for the volume flow rate, right? Volume, when it's divided by delta T, it's a rate. Volume flow rate. Okay, so how much volume of blood is getting through the blood vessel and how much time? Now, I'm not going to go, don't worry too much about that equation, except for one point. Except for one point, okay? By the way, this is called Poiseuille's equation. Say that fast, right? Okay, now, here's why you want to be concerned with this equation if you want a long and healthy life. So, here's a normal artery, normal blood flow. See how nice, see the nice cross section? Now here is what happens if you eat bad food and you don't exercise. All right? You get deposits or plaque. So now you have a narrowed artery, right? The blood is supposed to go through this entire cross section, but now it's only going through this part. Okay? Now, look at Poiseuille's equation. So let's just approximate. I'm not going to get super picky. Let's just make an approximation. So let's say that okay, this is completely open. Let's just say it's the radius divided by 2. All right? Okay, so I'm just saying that R, because of the plaque and everything, goes to R divided by 2. So it's like an effective radius, you know. So here is complete, and then here, you know, this is all covered with junk. Approximately, all right? So I'm just, again, it's not exactly R over 2, but let's just go for it, R over 2. Now notice, here's a R to the 4th power, right? Volume flow rate is proportional to the R to the 4th power. Okay, so if R goes to R over 2 because of all the plaque and everything, then delta V over delta T becomes R to the 4th. What's 1/2 to the 4th? 1/16. So it becomes 1/16, right? What it used to be. Okay, so that means you know, you're used to getting a certain amount of blood flow. If you have this horrible problem, you're only getting the flow rate is 1/16 what it would be if you had clear arteries. Now, That's horrible, right? I mean, your body needs oxygen and everything from the blood. And you get, it's way down, 1/16. So in order to compensate for this, what does the heart have to do? It has to pump harder, right? Is that a good thing? No. And what's probably going to happen to the blood pressure? It's going to increase. So is that a good thing? No. So what's the moral of the story? Eat good foods, right? And exercise so you don't have this kind of a problem. All right, let's review. All right, so with pressure in liquids and gases, we started out by talking about just liquids and gases that are steady, that aren't moving, right? Not moving. I didn't talk about these, but believe it or not, you know how they work now, right? We talked about the buoyant force, whether object sinks or floats, with the densities. So this was the fluids that were stationary. This is fluids that are moving. So continuity equation, Bernoulli's equation, and viscosity. All right, so just pressure, right? There's pressure everywhere, everywhere. And it's the same, the pressure is the same, doesn't matter the orientation of the pressure measuring device. In a liquid, the pressure increases with depth. In a gas, for a lab size container, the pressure is the same. So this is the important equation, right? With pressures that are not moving. Pressure increases with depth. It's linear with depth. And then we had to explore what did we mean by depth. So this is what, right? So this is where the liquid is, the top of the liquid. That's the depth. This is the depth. So the pressures are the same. Pressure's the same. Okay, atmospheric pressure. You got to be careful when you talk about pressure. Absolute atmospheric what? You got to be careful. So absolute pressure is atmospheric plus gauge. Okay, I went through this demo, sort of, right? The buoyant force is the weight of the fluid displaced. So this is the definition, you know, but it's sort of useless because you don't usually know the weight of the fluid displaced. So you just go over here, you just keep doing this, right? Weight is mg, mass is rho v, but then the volume of the fluid displaced is just the volume of the object submerged. And that's all. And the buoyant force does not depend on depth. By the way, you know, there is a buoyant force in this situation too. Here's the water, here's the object. So just pretend that's half, all right? So there's a buoyant force up here, right? Up, you know. But what would be the volume of the fluid displaced? The volume of the fluid displaced would be half of the volume of the ball. Okay? So that's why this is a nice way. So how much of the volume is submerged? Could be all. I mean, if it's completely submerged, it's the volume of the object. If it's half submerged, it's half of the volume of the object. Just whatever. Floating objects displace their own weight in the fluid, right? If something is floating, the buoyant force, which is the weight of the object, which is the weight of the fluid displaced, is the weight equals the weight of the object. Weight of the fluid displaced equals the weight of the object. Continuity equation, AV is constant. Cross-sectional area times velocity. Okay, Bernoulli equation looks horrible, right? It's just this. But again, if the object, like if the pipe is horizontal, then you just ignore that. Just say it's 0. So you just, right? So you just have this. All right? So just ignore that. And again, so if the velocity increases, the pressure decreases. And then we learned the Poiseuille equation and how to stay healthy. That's it. Thank you very much. We're done with this chapter.